Okay, thank you. This is the sort of other kind of functional programming talk, the one that doesn't have types in it, but I will promise you a bunch of parentheses. So one of the great things about presenting at conferences is that you submit an abstract, but you can basically talk about whatever you want. So last year I talked about the importance of contributing to your open source projects that you use at work. But this year, I want to take the opportunity to focus a little bit more on you as professionals, and there's kind of 2 points that I want to bring across. Generally, I prefer coding in a dynamically typed language. Most of you might prefer statically compiled typed languages. And we're probably both certain that our model, or our type system, is the best. And that it leads to code that's quicker to deploy to production with fewer bugs, and it's more malleable and all the rest of it. And we might even think that our programming languages are super relevant in that aspect. But the thing is that none of that really matters. What matters, if you want to create good code, you need to sleep and you need to be well rested. And the thing is that there are no studies that show significant improvements using this or that language, this or that type system, but there are tons of studies that show that sleep deprivation is super bad for you. And I want to not just talk about sleep, but also about rest, because it's important to rest, but rest does not mean inactivity. Rest is doing something else than what you do at work. So go out there, go skateboard, climb, go for a run, and let your subconscious work on your problems. Because it's a really nice way to solve problems, is to go out on a run and then come back, and problem is very often solved. And it also relieves you of stress. And I'm a fairly old developer. I'm pushing 48, I think. And people tend to say that technology is moving so fast these days that it's really hard to keep up. And to me, tech is not moving very fast. These days, I sit and work quite a bit on the front end, and this is sort of state of the art today. This is React with RxJS and all the rest of it. And I'm going to just go through this little example here, because the prior art, the thing that was re-implemented, was this, which was handlebars. And of course, being old, I programmed back in 1999 when we did JSPs. And it is the same thing. There was this thing called servlets. I don't know if you've used that, but that was definitely a sidetrack, because you do not want to print out HTML as strings. But then when I started out, I think that was in 1996, we used Perl. And we had template toolkit. And basically, it renders the same thing. It is the same HTML. And this is going back some 23 years, I think, if my math is halfway correct. And the thing with Perl was that we served it by using CGI scripts, right? Common Gateway Interface. And what was that? That was basically a web server that spawned a process, and then the whole Perl thing got compiled, and it got past the query parameters, and we rendered the results, right? Which sounds a little bit like lambdas, which has the exact same problems today, because lambdas need to have startup time that is 0. And that was a problem with our Perl script back in the days as well, that was as the scripts grew large, the compile time started to be big, and we took a performance hit on each and every request. So we solved that by going to application servers in Java, and now we're back again into lambdas. So, the main difference is that now we're programming JavaScript and not Perl. And you might ask if that's better or worse. And the thing you need to do is you need to start to focus on ideas and not on implementation. And if you do that, you'll see that most of the ideas, or the implementation that we have now, they're just implementation of ideas that have been there forever. When you in the JavaScript community find a new build tool, you have to ask yourself, how does this differ from Make that was done and finished in 1977 or something like that? More container stuff, new language. What kind of new ideas are you bringing to the table? And to do that, to sort of look at those ideas, you need to understand your problems. And that is, how is the new shiny thing going to solve the problems that you have? As a Norwegian programmer in Norway, I don't have big data. It's just not there. So I don't need to use the ideas that apply to big data. And it doesn't help that much to change your programming language if your problem is to find a market fit for your startup. And speaking of programming language, let's get to the meat of this talk. And I generally program in Clojure. That's my day job. And one of the reasons I really enjoy working in Clojure is that while it sort of fits my brain, it still also has changed forever the way that I think about programming and also how I program. And another thing that I find fascinating with Clojure is the way that it does not have a roadmap. We do not know what's going to be the next feature in Clojure. So when generics came out in Java 1.5, we were sort of all waiting for this. It was known, it was just expected, so when it sort of drops, it's an anticlimax. And I can imagine that it's a little bit like that in Scala as well. You know exactly what's coming in Scala 3, so by the time it's here, it's like, why wasn't it here earlier? And so what I want to talk to you today about is transducers, and that was a thing that was released in 2014 in Clojure. And they are, as described, a composable algorithmic transformation, which is a mouthful. And before we go into the details of these things, I want to have a look at today's agenda. And because it is scary standing in front of you, talking about composable algorithmic transformations, I want to sort of make this into a story of a timeline and see why they were made, what the motivations were, and how they ended up as they were. So we'll start with the history, and then talk about the transducers, and then look at the practical use cases. And before we get into this, there's a couple of things that I need to clarify. When I in Clojure talk about the function reduce, that is not the Scala version of reduce. It is the Scala fold left, and I think that's equivalent for Haskell as well. So fold left in Scala takes an initial value, whereas reduce in Scala does not. There's also this notion of arity. I don't know if you're familiar with that, but that just tells you how many arguments a function has, and we'll be talking a little bit about that as well. It's like that. Yeah. So, history and motivation. This is the timeline we'll be going through. In 2006, the initial commit for Clojure was, well, committed. And Clojure was based on the fact that Moore's law was no longer going to help us forward. So previously we could sort of rely on computers getting faster to make stuff go faster. What Rich Hickey thought was that we need to do more stuff in parallel because we're not going to get faster processors, but we're going to get more cores. And with that in mind, Clojure was implemented with a software transactional memory and also immutable data structures, which really lends themselves to doing stuff both concurrently and in parallel. It also has a sequence interface, which is basically a way of describing collections. So the sequence interface has two functions on it. It has the first and the rest. You could also maybe call it head and tail. And it's a very useful or normal way of dealing with collections in functional programming. It's a way to divide and conquer. You can structurally recurse on it. You do something on first, and then you recurse on the rest of it. Then in 2008, Guy Steele gives a talk called Organizing Functional Code for Parallel Execution. And what he notes in this talk is that it's extremely hard to make algorithms that are based on this first and rest abstraction to go much faster, because it's really, really hard to parallelize. Because if you want to parallelize things, let's skip that for a sec. But the thing he noted also was that the old tricks of trying to do stuff with fewer instructions doesn't really scale anymore. We're sort of down to the minimal set of instructions that we can manage to solve our problems in. So we need to parallelize. And this way of sort of doing map, so mapping over a collection, doesn't work anymore, because if you try to parallelize this, it just doesn't. So what you need to do is you need to divide and conquer. You need to have data structures and algorithms that lets you split the problems into 2 halves, and then 2 halves, and then 2 halves, and then you can solve the small bits, and then you can combine them together again to get the total result. So some years later, Rich Hickey dropped the Transducers library, which is basically his implementations of these ideas in Guy Steele's talk. And it comes with a couple of new things, or a couple of things that we need to talk about. The first thing is that it's an extreme focus on the reducing function. So if you have Scala's fold left, you see that there is this thing here, this operand, which takes a B and an A and returns a B. This is a reducing function. And in sort of my way, or my language, this is a thing that takes a whatever and takes some input, and it gives you a whatever. And to me, which may not be surprising to you, but to me, this is actually a thing that's almost a monoid. And I don't know much about these things, but it is supposed to be a semigroup with an identity element. And it is, so a monoid is an algebraic data structure, or structure with a single associative binary operation. And associativity here is important because it lets you group calculations. So it means that you can do some things on this side, something on that side, and then you can combine them again. And that's basically, this is our reducing function, right? And this is your monoid function, your monoid operator. And we find these the monoids, we find them a lot around. Multiplication is 1 over the numbers, and the identity value is 1 plus. But you have them for strings, you have them for maps. For maps, you have the operator is merge, with the empty map being the identity operator and such. So what you see is that grouping doesn't matter, but order does. And so when you want to use reduce to sum up all the numbers of a list, you're in fact reducing over the monoid that is plus 0 and the numbers in your collection. And you can, in Clojure, the reducing functions, they have to take 2 sets of arities. They have to take they have to have a 0 arity version, which produces the identity value. And then you have the 2 arity version, which combines the 2 things. So we could do this, and then we could go to this, which is the normal way of writing reduce in Clojure, because you can omit the seed value. And the good thing about that is then you reduce a little bit of coupling between the seed value and the thing that you are reducing over. So the insight that sort of I like to look for in my code is that whenever you have a monoid, you have a reducing function. Or if you look at it the other way, if you're calling reduce on something, then you are probably working somewhere in monoid land. And as one writes talks, one finds corner cases. And one such corner case is that in Clojure, we don't do operators. Everything is functions, which is nice. And less than or greater than, they are also functions, but they are not monoids, they're not reducing functions, because they only have the 2 arity version where you can say A less than B. But then we have this one function to the rescue, which is called monoid, which takes a 2 arity function and makes it into true reducing function, so you get the extra arity. The other thing that was introduced in the reducers library is this notion of reduced. And it gives you a way to short circuit a reducing operation. So imagine that you well, we'll get to an example, but the thing is that reduced is what you in algebra would call a zero object. And now I'm sort of on very, very, very thin ice. But this is one way you can describe a zero object. It's objects that lets you short circuit. And we use that a lot in our day-to-day programming. When you have, for example, you have an if test and you have A and B. So if A is false, you will never evaluate B, right? So for and, false is the zero operator. There's no need to continue calculating. And as such, for or, true is the zero object. And if you look at it, if you twist it around, then you will see that for and, true is the identity value, and for or, false is the identity value. So they're opposite there, and that sort of makes my head go around a little bit. So these are some zero objects for some operations. And you can use that in reduce if you want to multiply all the numbers in the list. You can see that if your number in your list is 0, then you can return reduced, actually of 0. That's an error in that code because any multiplication by 0 is 0. So there should be reduced 0 instead of reduced v there. And another insight that was gained is that, and that's I think known since quite a lot of time, is that you can implement map, filter, mapcat, all these sequence operations, you can implement them in terms of reduce or on full left. So that's what we'll do right now, is we'll try to refactor map in terms of reduce. And before we do that, we have this one function in Clojure called conj, which conjoins elements onto a list. And conj is, in fact, a reducing function. There's a bug in Clojure where the docstring for conj is not correct because it doesn't describe the zero arity function, or the zero arity version of it. But basically, conj of nothing gives you an empty list, and then conj of a collection and a thing gives you a new collection. So if we look at increasing all the numbers in the list by 1, you could do something like this, which is, in terms of reduce, it's written like that. So you end up with 2 reducing functions. You have one reducing function, which is basically taking the numbers and incrementing it by 1. And you have the other reducing function here, which is conj, which is ensuring that you assemble the list that you want to have as a result. We can extract this anonymous function into a function that's called mapping conj inc, which is a really bad name. And we move, so we've sort of moved one reducing function out. What we can do then is we can parameterize it. So we can leave the conj behind in the reduce. And now the mapping inc doesn't know anything about how it should assemble the result. It leaves that up to something that is parameterized. So now we can send this mapping inc over any type of collection as long as we parameterize it with the correct reducing function. And then we can also parameterize the inc like we had it. And then now we have a map that takes a function and returns a new function. And that new function takes a reducing function. So this is sort of a little bit around itself, right? We'll get back to this because this is sort of the meat of the thing. But the other thing that we needed to know with the reducers library is that every collection needs to know how to reduce itself. Because if a collection knows how to reduce itself, then we can implement very general map, filter, mapcat, what have you, in terms of reduce. And the last thing that came out of it was this function called fold, which is basically this thing where if you have a data structure that is partitionable into smaller pieces, you can call fold with an n, which tells you how big you want the partitions to be. Default for n here is 512, so it's for large collections. And you pass it a combining function, a reducing function, and a collection. And I think this sort of, if you think back to today's first talk, this is somewhere around the traversable thing that we saw, or not. Well, it starts to look like a lot of the things that we saw this morning. So in 2013, core async, or the last thing that this reducer library meant was that Rich Hickey had to re-implement map, filter, and such again. So now he has one set of map filters in the core library, then he has one more in the reducers library, and then core async comes along, which is basically Clojure's reply to streams. And he sees that he needs to implement map, filter again. And then he starts, as he does, he puts himself into the hammock and starts thinking a little bit. And then 2 years later, he comes up with transducers. And if we look at the map function that we derived earlier on, if we call that with map inc, what do we get? We get a function that accepts a reducing function, and it returns a reducing function, which is basically a function that takes whatever and some input, returns the new whatevers, and then returns a function that takes a new whatever and takes some input and returns a whatever. So this is basically what a transducer is. It's a transformation of reducing functions. So you could probably say that it's transformations of monoids. This maybe, I don't know. So what have we seen so far? Clojure was created on the premise or the bet that Moore's law would fail. Yet it was built with sequential data structures. Guy Steele claims that the way forward is parallelism, and Clojure introduces reducers as a response to this. And in that makes the data structures reduce themselves and focuses on the essence of the operations and not the conveyance, not how you assemble and disassemble your collections. And of course, you had to re-implement map and filter and such. Core async comes along, creates a need to re-implement map filter, and transducers are born. So what is then a transducer? It is basically, in its simple sense, it's a transformation of reducing functions. And how you do that is that you wrap a reducing function in another reducing function, and let's have a look at a couple of these. So this was the first one that I could the simplest one, which basically is an identity transducer. It does nothing. You give it a list and a reducing function, and it returns the values unchanged. You have map, which we saw. And you have something like filter, which is, as you'd expect, if the value satisfies the predicate, you continue reducing. Otherwise, you return the result. You're done. And if you worked in Ruby, how many people worked in Ruby? Maybe some. Then you would know that sort of the HTTP handling layer there is built on middlewares, and this is very, very, very close to how middlewares are done in Ruby and I guess Rails. So they're composable because these are functions that only accept one argument. So if you want to increment all the numbers and then filter the odd ones, you can compose these transducers. And what is kind of surprising, to me at least, when you look at it, is that this returns 1357, which indicates that the increment is done before the filter. whereas functional composition normally runs from, I can't do the difference between left and right, but it runs from right to left. So let's have a look at what this means, or why it is like that, right? So we have our two our two functions, map and filter. And we can inline, if we unparameterize them, I don't know if that is a word, but you can unparameterize them, so you inline the functions that we are mapping with and filtering with. We get something like this. So now we have our transducers. And this is the thing, it gives us this. So we're composing map inc and filter odd. So if we focus on the composition of this, we can also unparameterize the conj bit, which leaves us at something like this. And then we can substitute this in for the comp, so we get something like that, which ends up in this. So you see here that the way that the code is being executed, we do actually, right here. Here we see that the inc is actually called before the filtering bit. So that is, although the functions are composed from, are run from right to left, the transformations are done from left to right, which is a little bit surprising to me. But it's good because it sort of maps up nicely with the other way that we write Clojure. So is this in any way practical? Well, it's very practical for operations or processes that are stepwise, because we have this reducing function, so it's very easy to apply it to either streams or collections or what have you. They're composable, so we can do stuff like this. And one of the things that I would have done if this talk were tomorrow instead of today was to take the examples from this morning and rewrite them in terms of transducers, but I didn't have time to do that because I wanted to focus on the talks. So they're composable, but they're also sort of associative composable. So you can take like a composed bunch of transducers and you can add another transducer to it. So you can really build stuff from smaller components. They're conveyance agnostic, which means that they don't care if they're transducing on a stream or a collection or something, or if whatever implements something that's reducible. And this makes testing very easy. Because if you have a transducer like this, and you want to apply it onto a core async channel or a stream, you can write the unit test on a normal collection. So you don't have to mock out your streams and stuff, and you don't have to teach yourself, like today I'm programming a lot of RxJS, and I have to teach myself a whole new set of map, filter, reduce, and reduce is called scan, and life is terrible. But this is very good for testing. And it's also very efficient because it doesn't create intermediate collections. As you saw, there is no, when you map over something, you will produce another collection. And then when you filter again, you will create yet another collection. So if your collections are large, then that is inefficient. But here, you're not creating any intermediate collections. So if you look at this code here where we take only one element of the computation that we did, we're only calling inc once, and we're only calling inc once because the first number will be 0, and then we inc it, it's 1, and then it's odd, and then we're done. Whereas if you had a bunch of numbers and you did this normal way, you would loop over all the numbers. Like so. Yeah.
The last thing you said is that I don't know about Clojure or this, but is it because Lisp or Clojure is inherently lazy, or is it specific to this library?
Clojure is lazy, yes. But the laziness, we'll take that after the talk because it's another subject. Yeah. Transducers, they are not lazy. They are eager. They will pull the result Yeah. And as such, they work really nicely for when you talk to external resources like databases. Because if you in Clojure have a database and you have the connection and you wrap it inside a with open and you map over the things and you return that result, you get a lazy result, and the lazy result is not evaluated before the connection is closed and you're outside of the database and things blow up. If you ever worked with Hibernate and you've had open session in view, then you know what I'm talking about. But Transducers lets you do this very eagerly, and that is a very good thing. So, in summary, languages and type systems don't matter. Sleep does. Make sure that you come to work well rested. And for the ones of you who have small kids, babies arriving, then you're not going to be doing your best work the next couple of months, I don't think. Use languages that change the way you think, and also go to conferences that change the way you think. To me, it's very exciting to be here at flatMap because I get exposed to types, and although I can see that we're doing basically the same thing, I can see that we're doing it from two different perspectives. And it, as a side note, it also reflects a little bit on how I like to learn. Some people like to learn from sort of the atomic and the first principles and then build up. So down here, you don't really know what you're going to use the monoid for, but then after a while, you figure out that, oh, I can add numbers with them. Whereas I'm more practical, I would say, so I have some numbers that I need to add, so I need to have plus. And then later on, I can see that, oh yeah, that is a monoid, and that's cool because then I have these other properties that come along with it. Parallelism, that is the way forward. Even though your AWS EC2 instances don't have that many cores, they're actually running on super big machines with a lot of cores. So although your systems are running, your microservices are like, no, there's no need to parallelize because we only have two processes here. That is not the truth. We just put a layer of Kubernetes on top of the super duper machine that we're running on. Go looking for monoids. Especially if you're, if you do reduce, then monoids are cool things. And I think it's worth noting that as mathematicians, it seems to me, they have a bunch of abstractions, and then they go looking to see if their domain fits either one of these abstractions. Whereas programmers, we tend to create our own abstractions to fit the problem. And that means that we don't have any general laws that work on the abstractions. And I think a talk that was given here by Erik a couple of years ago was on state machines and regular expressions. And it got me thinking a lot that, we're solving a lot of problems in very bespoke manners instead of looking at them and see if we can map them onto any of these known abstractions, which we have really good ways of solving. And I guess that's what you call lifting stuff up a little bit. Small doses of algebra can be fun. Not too many, not too big, but it's really interesting for me to see that, oh, this is a monoid, this thing that I've been working with forever. And I've sort of been scared of algebra since I didn't finish that in university, I think. So that's all I had. I won't be taking many questions, but I'll leave you with this list of references, and I'll post the slides on GitHub. Thank you.